Nuclear energy. These two words conjure powerful images, a force born from the very heart of matter. It holds the power to illuminate our civilization, to power our cities, our homes, our dreams. It mirrors the energy that fuels the stars themselves, a boundless source waiting to be tapped. This is the bright face of the atom, a promise of an almost magical abundance. But this energy has another side, a darker aspect. The same fundamental forces can be unleashed for destruction, creating weapons of unimaginable horror, weapons capable of erasing cities in an instant, leaving behind only shadows and lingering poisons. This inherent duality defines nuclear energy. It is a cosmic fire given into human hands, a tool of immense potential for good or for ill, our greatest triumph or our ultimate folly. The story of nuclear energy is a human story. It is a tale of brilliant discovery and profound error. How we manage this power will shape our destiny. The question is, are we wise enough to use it? Our atomic journey began not with a bang, but a whisper. In the late 19th century, science was buzzing. In 1896, Henri Becquerel, a French scientist, made an odd find. He was studying uranium salts and their fluorescence. He left some uranium near photographic plates. The plates were wrapped in thick black paper, yet they became fogged as if exposed to light. Something invisible was emanating from the uranium. This mystery captivated a brilliant young Polish student in Paris. Her name was Maria Skłodowska, later Marie Curie. She, along with her husband Pierre Curie, took up the challenge. They processed tons of pitchblende ore. Their dedication was extraordinary, their conditions poor. They were driven by the pure pursuit of knowledge. Their persistence paid off spectacularly. Marie and Pierre discovered two new elements: polonium, named after Marie's native Poland, and radium, an intensely radioactive substance. Radium glowed faintly in the dark, a ghostly light. Marie Curie coined the term radioactivity to describe this behavior. She theorized that atoms were not immutable. They could spontaneously disintegrate, releasing energy. These pioneers worked at great personal risk. Their groundbreaking work opened a new realm of physics. The early whispers of radioactivity grew into a roar. In 1938, Hahn and Strassmann discovered nuclear fission in Germany. Splitting a uranium atom released a burst of energy, and crucially it released more neutrons. These neutrons could split more atoms, a chain reaction. The possibility of a weapon of immense power became clear, and the world was teetering on the brink of global war, fearful that Nazi Germany might develop an atomic bomb first. Scientists, many of them refugees from fascism, alerted the US government. Albert Einstein signed a letter to President Roosevelt. This spurred the creation of the Manhattan Project in 1942, a colossal, top-secret undertaking, its sole purpose to build an atomic weapon before the enemy. Tens of thousands of people worked on it, across hidden sites like Oak Ridge, Hanford, and Los Alamos. At Los Alamos, New Mexico, a team of brilliant minds gathered. Led by the enigmatic physicist J. Robert Oppenheimer, they raced against time, grappling with complex scientific puzzles. On July 16, 1945, in the desolate Jornada del Muerto desert, the culmination of their efforts, the Trinity test, the world's first nuclear detonation, a searing flash of light brighter than 1,000 suns. The atomic age had arrived, with all its terrible implications. The terrible power demonstrated in the New Mexico desert. It was soon deployed in the theater of war. World War II in Europe had ended, but the conflict with Imperial Japan continued fiercely. US leaders faced a grim calculation. An invasion of Japan could cost hundreds of thousands of lives on both sides. President Harry S. Truman made the decision to use the new atomic bomb to force a swift surrender. On August 6, 1945, a B-29 bomber named Enola Gay. It flew high above the Japanese city of Hiroshima. At 8:15 a.m. it released its payload Little Boy, an atomic bomb fueled by uranium-235. The explosion was catastrophic, instantaneous, a blinding flash, intense heat, a crushing blast wave. The city center was obliterated. An estimated 70,000 to 80,000 people died immediately. Many more succumbed to injuries and radiation sickness in the following weeks and months. The world was stunned, but Japan did not surrender, so a second atomic strike was ordered. On August 9, 1945, another B-29 Bockscar. It carried Fat Man, a plutonium implosion bomb. The bomb was dropped on the secondary target Nagasaki. Another city was devastated, another wave of death and suffering. Japan announced its unconditional surrender on August 15th. Section 5. The Atom's Promise, a new era of peaceful power. After the horrors of war, a new question arose. Could this awesome atomic power be harnessed for peace? Could it be used to build, rather than destroy? In 1953, U.S. President Dwight D. Eisenhower delivered a landmark speech before the United Nations General Assembly. He called it Atoms for Peace. He proposed international cooperation to develop peaceful uses of nuclear energy to share its benefits with the world. This vision sparked optimism and excitement. The atom, once a symbol of war, could become a symbol of progress. Scientists and engineers dreamed of a future powered by nuclear reactors, generating vast amounts of electricity without the polluting smoke of coal and oil. Nuclear energy promised to power industries, to desalinate seawater for arid lands, to drive ships across oceans and probes into space. It seemed like a pathway to a brighter, cleaner future. Section 6. When safeguards fail, the specters of Chernobyl and Fukushima. The optimistic march of nuclear power faced stark setbacks. Accidents, though rare, could have catastrophic consequences. They served as grim reminders of the risks involved. On April 26, 1986, the world witnessed such a disaster at the Chernobyl nuclear power plant in Soviet Ukraine, during a poorly designed safety test on reactor number 4. A sudden power surge led to a series of explosions, and a massive fire that released radioactive materials. The reactor core was exposed to the atmosphere. The Chernobyl disaster was a profound shock. A plume of radioactive fallout spread across much of Europe, contaminating land, water, and food supplies. Over 350,000 people were evacuated from contaminated areas. An exclusion zone was established around the plant. Dozens of plant workers and firefighters died from acute radiation sickness. The long-term health effects, including increased cancer rates, continue to be studied and debated. Chernobyl shattered public confidence in nuclear safety. A quarter-century later, another major nuclear accident occurred. On March 11, 2011, a massive earthquake struck off the coast of Japan. It triggered a devastating tsunami. The Fukushima Daiichi nuclear power plant lay directly in its path. The tsunami overwhelmed the plant's seawalls. It flooded the backup generators, causing a station blackout. Section 7. Chasing the Sun, the quest for nuclear fusion. The nuclear power we use today relies on fission, the splitting of heavy atomic nuclei like uranium. This process releases energy but also creates long-lived radioactive waste, and carries the risk of meltdowns if not carefully controlled. But there's another, even more powerful nuclear process, one that powers our sun and all the stars in the universe. It's called nuclear fusion. The joining of light atomic nuclei like hydrogen isotopes to form a heavier nucleus, releasing immense energy. Fusion power holds incredible promise for humanity. Its fuel sources are virtually inexhaustible. Deuterium can be extracted from seawater. Tritium, another fuel component, can be bred from lithium, which is also abundant in the Earth's crust. Fusion reactions produce helium, an inert gas. They do not produce greenhouse gases, and crucially, they generate far less long-lived radioactive waste than fission. A runaway chain reaction, like in fission, is physically impossible. Achieving controlled fusion on Earth is an immense scientific challenge. It requires creating and confining a plasma, a state of matter where atoms are stripped of their electrons, at temperatures exceeding 100 million degrees Celsius. No physical material can withstand such heat, so scientists use powerful magnetic fields. Section 8. Smarter atoms, advanced fission and modular innovations. While the dream of fusion beckons in the distance, fission technology itself is not standing still. Scientists and engineers are developing new generations of fission reactors. These advanced designs aim to be inherently safer, more efficient in their use of fuel, and to produce significantly less or less problematic radioactive waste. They learn from the lessons of the past, incorporating innovative features to address old concerns, and to make nuclear power a more sustainable option. These Generation 4 reactor concepts are diverse. They include designs like molten salt reactors, MSRs, where fuel is dissolved in a molten fluoride or chloride salt. This salt acts as both fuel and coolant. MSRs can operate at lower pressures and higher temperatures, offering enhanced safety and efficiency. Some MSR designs can even consume existing nuclear waste, or thorium, an alternative nuclear fuel. Other concepts include high-temperature gas-cooled reactors and lead-cooled fast reactors. Another exciting area is the development of small modular reactors, SMRs. These are typically defined as reactors producing up to 300 megawatts of electricity, much smaller than traditional gigawatt-scale plants. Their key advantage is modularity. Components can be factory manufactured and shipped to a site for assembly. This could reduce construction times and costs. Section 9. The human element. Our nuclear choices, our shared future. We have journeyed from the atom's first discovery, through its awesome power and its profound dangers. From Becquerel's glowing salts to the fires of Trinity, from the devastation of Hiroshima and Nagasaki, to the promise of atoms for peace and the hum of power plants, and onward to the challenges of Chernobyl and Fukushima. Now we look towards new horizons like fusion and advanced fission. The story of nuclear energy is deeply intertwined with our own. a reflection of our curiosity, our ingenuity, and our fallibility. Nuclear energy presents humanity with a persistent dilemma. It is a source of immense, concentrated power, a potential solution to our growing energy demands, a tool that could help us combat climate change by providing carbon-free electricity on a massive scale. Yet, it carries undeniable risks. The specter of catastrophic accidents, however small the probability, the challenge of securely managing radioactive waste for millennia, and the ever-present danger of nuclear weapons proliferation. The atom remains a double-edged sword. The future path of nuclear energy is not fixed. It will be determined by the choices we make, as individuals, as nations, as a global society. These choices must be informed by science.